Hello everybody, and welcome to the latest edition of the Physics Corner, a series of videos intended to help students set up and solve physics problems in introductory classes. I'm your host, Dr. Christopher Sorolla. Today, we want to look at a two-dimensional motion problem, or a 2D projectile motion problem, if you will, to show how to set up problems that A, are acting in more than one dimension at a time, and B, how to take all these equations that we've been throwing at you lately and put them to use. So here is our situation. Let's imagine that there's a group of campers that get stuck in the woods. And they get stuck in such a way that even though people can spot them from the air, they have no immediate way of getting to them. So in order to keep the campers supplied with the food that they need, an airplane is sent to drop a package of supplies, food and other items that they might need. So the question is then, how or when, if you will, should the plane make the drop? Now the plane can't stop, right? So the plane has to be flying across, if you will, or over the campers while this happens. So in our picture here, we see here's the plane moving forward horizontally at some initial speed. We'll call that Vx naught for the moment. You'll see why we do that in just a bit. Here's our package. Because the package is part of the plane, the package at the moment is sharing the same velocity as the plane is. Once we release the package, it will be in free fall. But at the moment, it's sharing the same speed. The plane is also soon to be a height above the ground like this, okay? And we will be determining the distance from the package to the campers this way. This, by the way, is not drawn to scale. We're obviously also making some very big assumptions. One very important assumption is we're going to ignore the effects of air resistance on the package. That turns out to be very problematic in actual practice for several reasons. One is, if we actually drop the package like this in perfect free fall, it would probably be hitting so fast that it would actually damage the contents. Of course, we don't want that. So there's a likelihood that a parachute or some other way of slowing the package down would be attached to the package. Also, we're ignoring the effect of wind. We're going to assume for purposes of the problem that the ground is perfectly level, that the plane also is traveling perfectly level or horizontal, and so on and so forth. So the purpose of this problem isn't to be too realistic about the problem. It's more to show how you get started on a problem, given some initial assumptions. That's a decently complicated problem. This is a two-dimensional motion problem, and we need to show how you might approach this, all right? By the way, if we were to do this more realistically, we would need a lot more information. Turns out that if you were to do this realistically to properly account for air drag and other factors, you would actually need to do computer calculations. It is not a kind of problem that can be solved simply through equations alone. You would actually need to do some calculations with a computer program to actually simulate this properly. Now, as far as the people on the plane are concerned, there's of course a pilot who's flying the plane. We're also going to have a technician whose job it is to use a telescope and a protractor to sight in the campers. So I want you to imagine the following. The technician aboard the plane is trying to look towards the campers. Something like this, all right, in that particular direction. When the campers reach a certain angle or certain distance away from the plane, I should start there first, then it's safe for the technician to drop the package, and the package will land close to the campers. Again, assuming all these other things are negligible or things we can safely ignore. Which means what? It means we are, if you look carefully, creating a bit of a right triangle here, right? So we have a right triangle that we've formed. We have a height for one leg of the triangle here, and we have a distance called delta x here. Now, the height is known. The plane can use its own equipment, altimeter, to measure the height above the ground, but there's no way to measure ahead of time how far it is from the campers from here to here. So we're going to have to calculate that, all right? Second thing is, the technician aboard the plane isn't measuring this directly or isn't sighting indirectly. What the technician in the plane is doing is using a telescope or some other sight to view the campers. So imagine you're using a telescope of sorts right here. You can imagine a telescope with a lens on it, something like that, and it's pointing towards the campers, and the technician will see this going at an angle below the horizon or below the horizontal, like that. So when the campers come into view of the telescope at a specific angle, then the technician will know it's safe to drop the package. So what we're actually after, strangely enough in this case, is this angle of sighting, right? Now, a couple things about this. First off, we've already mentioned this forms a right triangle, but if you look at what I've got drawn so far, this angle isn't inside the right triangle, right? But you might also remember this little ditty from plane geometry. We have parallel lines here, here, and here, and we have another straight line segment that goes across like that. There's an interesting little idea in geometry that the interior angles between parallel lines is the same. So in other words, this angle here is identical to this angle here. So if we can determine this angle, then we've got that angle, then the technician can make the safe drop. All right, so what goes into this particular triangle? Well, this is a distance triangle, if you will. And so we already know the height, or the plane will know the height. If we can determine this distance here, then we can calculate the angle, right? So that's the strategy that we're going to follow, right? So there's the idea. Now, specifically, since we're on this topic, we might as well set this up. If you look at this triangle, this is the opposite side, that's the adjacent side. Tangent of our angle, by definition, is opposite over adjacent. And if we want to solve then for the specific angle, we take the inverse tangent of that. Now, instead of opposite, it's really the height. And instead of adjacent, it's this delta x. So the calculation we need to make is this one here. So we have the height given to us. Can we find this delta x from other information? That's what we want to see if we can do. Okay, so again, we have to re-emphasize this. This is not a realistic problem in a lot of ways. We are showing how to do such a calculation. And by the way, as another quick aside, this kind of exact thing was done in the past, especially during, say, World War II, when bombardiers, that's our technician here, were trying to determine where to release bombs out of the plane to hit their targets. They actually enlisted physicists behind the scenes to do calculations. Remember, if we're doing these as realistic calculations, they're a lot more involved than what we're doing here. So, but let's do the simple version. You'll find that's complicated enough. Okay, so this is a two-dimensional problem. And with a lot of our problems that are more than trivial, we should set up a table of known and unknown quantities to help us figure all this out. So let's do that. So what is known and what is unknown? So as we tend to do in a lot of these problems, for simplicity, we're going to assume that the effect of gravity, little g, is equal to 10 meters per second squared. So I'm going to round that off. Again, if you're doing this as an actual calculation for a real case, you would use your more precise value of this, right? But this is a demonstration problem. We're showing how it's done. And of course, little g points straight down, right? What else do we know? Well, we go to the problem and read, and it says the plane is moving horizontally towards the party at 100 meters per second. When the package is released, that is also its speed. So its original speed in the horizontal direction, we'll call that Vx naught, will be 100 meters per second, right? What else do we have? Well, we have the height above the ground, okay? Now, I'm going to call that in a different context delta y in just a moment, so I'll go ahead and write that there. And that is given to us as 1,000 meters. So we have that. Okay. Are there any things that we are given or are hinted at that we can assume even though the numbers aren't specifically written out? We already did that for g. What else can we do? Well, it's moving horizontally, which means, at least to begin with, the package has no vertical motion. So the initial vertical motion, which we can call Vy naught of the package, is 0, right? So we can assume that. Now, of course, once we drop it, then it will get faster and faster as it falls, right? But to start with, the initial vertical speed is 0. We can also talk a little bit about the acceleration of the plane in both directions, the package. We have this as g, and that is really the acceleration in the vertical direction, right? So we'll call that a y coming up. And what about the acceleration in x? Well, let's assume that there is no air drag. Now again, this is not a realistic problem to that extent. In reality, air drag would be an important component of what we're doing. We're not doing that here, just to show how this might get started. So if air drag is not an important idea, then we can ignore any accelerations we might get because of air drag. And so in the horizontal direction, at least, we can assume the acceleration will be 0 of our package. Okay. Again, these numbers all apply to the package. Once the package is dropped out of the plane will fly on its merry way, and we don't need to worry about what it's doing. It's the package that we're concerned with. So all these numbers apply to the package. All right. What about unknowns? Well, a couple things we don't know. For example, quite obviously, we don't know how far it is to the campers. So that's something we need to find, right? So that's one of the items we're going to look for. What's another item that we don't know? We don't know, for example, how fast the package will go when it lands. So the final velocity in the y direction is unknown. And the overall speed of the package will be unknown like that, okay? We do know the final velocity in the x direction. I'll talk about that in a moment. Right? What's something else we don't know? Well, we don't know, it's not given, how much time it will take for the package to fall to the ground. So we'll label that with the little letter t. Okay? And of course, the thing that we're searching for in the long run is the angle. So this angle here is an unknown. So we have many unknowns and many knowns. All right, I've already been hinting at this. This would probably be a good idea to talk about at the beginning. Let's set up some coordinates. So whenever you do questions that involve more than one direction, even if you do a one-dimensional problem, it's a good idea, but especially for problems that involve more than one dimension, it's always a good idea very early on in a problem to set up a system of coordinates. In other words, x's and y directions. Let's do that. So going forward, we'll call it that the positive direction in x. We can do it that way. And because the package is dropping down to the ground, because all the motions of the packages is going to be downwards, I'm going to call going down the positive y direction. That is a thing we can do as long as the angle between our coordinates is a right angle. This is a legitimate thing to say. Now, having said that, having started with this, we need to treat all of our numbers when we calculate in this fashion. We can't go back later on and say, oh, we really meant the direction is supposed to be positive up, or that this number is negative after all. No, once you make this choice, you have to stick with it. But this turns out this will be a convenient choice for us, and we'll see. Okay, so we're after theta, all right? I already have written down tangent here to give you an idea where we're going, but we need to find delta x. So it will help us a little bit if we bring forward equations of motion. So let's take a look at some equations of motion, see if they can be of some assistance to us. So first off, here's delta x. There it is. In fact, delta x shows up in several different equations, right? This one here, it's not in at all, so we can ignore that for the moment. And in fact, this is all the delta x or x-related motion equations here. All the y stuff is over there. Now, we might need y for other purposes, but let's talk about delta x right now. So for delta x, delta equals what? Well, if we take a look, Vx naught, that's given, right? The time we don't know yet. The acceleration is 0. If this acceleration is 0, this entire term disappears, and the only thing we're going to have for an x equation is delta x equals Vx naught t. Okay, well, that's interesting. Let's write that down. So delta x equals Vx naught t, like that. All right. Second thing to talk about, and I'll show it off with an equation, but we can also make an argument physically for this. What about the final x velocity? I already hinted at it. Final x velocity here, Vxf, is equal to Vx naught, the original velocity in x, plus axt. But again, if there's no important air drag or wind, that term disappears, and the final velocity in horizontal is the same as the initial or original velocity in horizontal. It doesn't change. So we don't need to worry about that. We already have that number. Okay. That's a nice thing. That'll come in very handy. And what that also means is that these two statements then, and this second statement then doesn't even involve a calculation, are all the information we're going to drag out of these equations. Okay. So let's look back at our equation that we've written so far. So we know that we need this equation to solve for angle. We already have the height, or delta y, if you will. Delta x is what we're looking for. Here's delta x. We have Vx naught. That's good. Here it is. But we don't have time yet. So we need another way, another method to find time. We can't get time from the horizontal. We've already looked at all the horizontal equations, and there's no way in which we can use any of that information from x only to determine the time. That's where the y component, the vertical component, comes into play. So let's bring back our equations of motion and see something about that. So let's look at this first equation here, see if that'll help. So delta y, or h if you will, the height, that is a given, right? That's the 1,000 meters. Vy naught is 0. We're simply dropping the package out of a plane, so that term is 0. We have a 1/2. Ay, that's gravity. The acceleration in the vertical direction is little g. So let's write this down then and see if that helps. So that equation becomes delta y equals 1/2 gt squared, like that. And if we look at this equation, we know delta y, we know g. We can calculate time from this equation. If we have time, we can use time to calculate delta x from this equation. And if we have delta x, we can calculate our angle from that. So notice the thought process we're going through as a general idea. We're kind of working our way backwards, if we will. So what do as an overall thing? We have identified what it is we're looking for. We're looking for the angle. That's what the technician will physically be looking through, measuring in order to make the drop. So that's what we're looking for ultimately, all right? How do we get that angle? We need these two distances, okay? This distance is given. How do we get this distance? Oh, we go to this equation. How do we get, and so on and so forth, right? So you can see that we have to kind of dig our way through the equations until we reach a point where we have all the information we need to calculate something. Once we have that, then we can run the clock forward again, if you will, and go ahead and do our calculations. So that is our strategy. It's look at what you need, identify what it is that you need, and then keep going through several equations if you need to finally hit the bottom of the calculations where you have all the information you can have to start calculating numbers. Then race those equations back the other direction, so to speak, to do the calculations and get what you want. All right, so with that in mind, let's do some calculations, everybody. So let me write down this first one that we're going to play with. Delta y equals 1/2 gt squared. And again, just to remind everybody of how we're doing this, we're going to set this up so that we're just rounding off g to 10. Again, this is a demonstration problem. It's not a calculation for real in any case. So, but let's go ahead and do it. So let's do some algebra. Let's see here. So we need to multiply both sides by 2 to move the 1/2 over, and divide both sides by g. So our algebra step would then be multiply the entire equation by 2 and divide by g. If we do that, this 2 cancels a 1/2 here, this g cancels a g here, and so the right-hand side, the 1/2 and the g are gone. Over here, we'll have a 2 multiplied by the delta y and divided by the g. So this means this equation now becomes this. We have t squared by itself, and then there's a 2 delta y over g, like that. Next step, of course, is take the square root of both sides. So let's do that. And my solution looks like this. So this already is our algebra solution. So any height that you have for the plane, we have a specific number for our problem that we've given, but this will work for any height. Again, assuming air drag is negligible, which we're doing. All right, let's plug in our numbers. So 2, the height is 1,000 meters. We're rounding off g to 10 meters per second squared, like that. Okay. So 2 times 1,000 is 2,000. 2,000 divided by 10 is 200. So that'll be our number. If we look carefully, this is something to watch for. Let's check the units. So meters here divides by meters here, they cancel. So the meters disappear, which is good because we don't want meters in our answer for time, right? How about this one? This looks a little tricky, but we have 1 divided by seconds squared for units, which means if you take a number and divide it twice in a row like that, it comes back up to the numerator. So inside the square root sign, it's 200 seconds squared like that. And again, remember, we treat units in a very similar fashion to the way we treat numbers, okay? So if we take a square root of this, we'll make that work. All right, square root of 200 is 14.1, and second squared square rooted is seconds, of course. And there's our first answer. The time it takes for the package to fall with no air drag is just a touch over 14 seconds. Okay, interesting result already. All right, what's the next task? Well, let's go back to our equations here to show off what we were doing. Remind ourselves. So we have this result. Now that we have time, we can put the time in to get delta x, the distance from right below the plane to the campers. So delta x equals Vx naught t. This calculation is pretty easy to see. It turns out it was 100 meters per second for the speed of the plane, 14.1 seconds. Now I really need a calculator for this one, right, folks? And we get this number of meters. And it looks like that. All right. So last task then is to calculate our angle of vision. And we already talked about where that angle comes from. It's the inverse tangent of delta y over delta x. Or if you prefer, the way I originally had it written, is height over delta x. They're the same thing. Height and delta y are. And what are the numbers then? Height was given as 1,000 meters. The delta x is 1410 meters, like that. Now, one thing to make sure everybody reminds themselves to do, in a lot of calculators, most calculators are set to what we call degree mode, which is when you do an inverse tangent or inverse sine or cosine, you should get an answer back in degrees. But some calculator brands, Texas Instruments, for example, are notorious for this, default to a different kind of unit called the radian. You haven't reached a radian yet in this class. You will at some point, but for now we're not using it. We want degrees. So make sure that your calculator is going to give you a calculation that gives you answers in degrees. Otherwise, your number will look a little weird, if nothing else. Right? When we do this, though, we do an inverse tangent of this calculation. Notice the meters cancel inside the brackets here, right? So it goes away. We want that to happen. We'll come up with an angle of 35.3 degrees. And that is the angle. Okay. Again, one last time, this is not a very realistic problem, but it is a problem that combines a lot of our knowledge that we want to develop with two-dimensional motion. So if air resistance was negligible, if there's no wind, if the ground is level, and so on and so forth, these are the numbers and the formulas that we would apply. This is a starting point. One of the reasons to do this is because when physics people do problems, they always do problems in the simplest possible fashion that would give you some realistic answer, some answer that's at least close to what you want. And then you can go ahead and refine that. You can go ahead and then start including the effects of, say, air drag or wind or other issues that you need to include. And in a lot of cases, those will end up being tweaks. This will end up being small variations or adjustments to your answer that you had to start with. So we end up starting with the simple versions always. Also, for our purposes here in this class or this set of videos, these videos are specifically for introductory physics students using algebra and trigonometry, not calculus. And so, if we want to use calculus, we could do this a little bit further. We're not going to do that. We're going to instead stick with the algebra, and at that level, it's probably best to leave it as. Also, as I said before, because it's a two-dimensional problem, if you invoke air drag, you would actually have to run a computer program or a spreadsheet in order to get a numerically calculated answer rather than just solving a simple equation. So it's a lot more complicated and was complicated back in the day for those World War II pilots. So just last comments there. In any case, this is a way to handle a problem like this. One last comment to make before we go today. This is sometimes referred to as a projectile motion problem. What is a projectile? A projectile is an object that is given some initial push or throw, if you will, and then left to simply go off on its own. So if I take a rock and I drop it, or if I take a rock and I throw it, if I take a package and drop it from a plane like this, once we make the drop, that object is now a projectile. It's not acting of its own volition. It's only responding to the outside forces, like, say, gravity or air drag if you include it, and that's it. An object, on the other hand, that is self-propelled, like an airplane, is not a projectile. So that is not simply allowing things to happen to itself. It's also participating, if you will, in all that. And so planes, rockets, objects like that, which are self-propelled, at least to some extent, are not considered projectiles in physics. So if you hear that term, projectiles and projectile motion, this is an example of that sort of situation. All right. Hey, everybody. Technical assistance for this program is supplied by Cindy Geltraw and Sophia Turner. Funding comes from the University of Mississippi and University of Southern Mississippi. We record in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla. Thank you for your attention, everybody, and clear skies.